Hello everyone, I'm Professor Harrison, and welcome back to our module on statistical inference. Today we're covering one-tailed versus two-tailed tests, and the core logic of what it actually means when a test fails to find significance. We're following Bess, an investigative journalist on a cold case that she can't let go, and today she's digging into a research controversy over analyst upgrades. Two research teams ran a hypothesis test on the same analyst upgrade data and came to opposite conclusions. To figure things out, she pulls up her case file. Both teams are testing the same question. Do sell-side analyst upgrades predict positive abnormal returns? The null hypothesis is the same for both, that upgrades have no effect. Both teams end up with the same test statistic. What is different is how they structured the alternative. That choice determines how the p-value gets computed. We already know from the p-value video that the p-value measures how likely a result at least extreme as this value would be under the null. That tail choice determines what counts as extreme. A two-tailed test asks whether the average return is different from zero in either direction. The alternative is that the mean is not equal to zero. So if we wanted to define extreme, it would mean far from zero in either direction. So the p-value includes both tails of the t-distribution, results that are unusually high and the results that are unusually low. A one-tailed test asks whether the average return is positive specifically. The alternative is that the mean is greater than zero. So if we were to try to define extreme, it would mean only things that are far in the positive direction. So the p-value includes just one tail. For a symmetric distribution like the t-distribution, the one-tailed p-value is exactly half the two-tailed p-value. The same test statistic and the same data, but the one-tailed p-value is smaller because you are only counting probability mass in one direction. In the analyst upgrade study, the test statistic was the same for both teams, but the first team computed a one-tailed p-value which fell below the significance level. They rejected the null. The second team computed a two-tailed p-value which was exactly twice as large, and it did not clear the significance level. They failed to reject. With the same data, same test statistic, they just had a different p-value and came to a different conclusion. The defining property is this. A one-tailed test is correct when you have a directional prediction grounded in theory, established before you even collect your data. For analyst upgrades, that prediction is obvious. An upgrade is a positive signal, so the theory says the price should go up, not go down. The one-tailed setup is the correct one. One common mistake is choosing the one-tailed test after you already have your results because you want the p-value to show something that you prefer. This is called p-hacking, and in this circumstance you're not testing a theory, you're working backwards to get the answer you want. This approach is incorrect, and the choice between a one- and two-tailed test should always be grounded into theory, not based on what result you're trying to find. So the first team had the right setup. Analyst upgrades are a positive thing, so they should lead to positive returns. In this circumstance, the one-tailed test is the proper one, and this ends up getting us past our confidence threshold, making it so that we reject the null, whereas the two-tailed test would not have. Bess also notices that the second team made a further mistake. They took their non-significant result and concluded that the analyst upgrades have no real effect. That conclusion, however, does not exactly follow. Failing to reject the null hypothesis does not mean that the null is true. A p-value above the significance level does not tell you that the true effect is zero. It tells you the data did not provide enough evidence to reject the default, which are two very different things. Think about what could produce a p-value above the threshold even when a real effect exists. A small sample with too little power can do this easily. A noisy measure that ends up burying the signal can also do this. Any of those can push the p-value above the significance level even when something real is there. Failing to reject is not a confirmation that the null hypothesis is true, it is simply running out of evidence to reject it. The correct conclusion from the second team's non-significant results is that this data does not provide enough evidence to conclude that upgrades predict abnormal returns, not that upgrades have no effect. Those are not the same sentence, and in finance they end up having very different consequences for investors and for anyone who relies on this research. In her article, Bess explains this to her readers. The controversy was never about the data. Both teams had the same numbers. The first team was the one, however, that set up their test correctly. It was a directional prediction grounded in theory, specified before they even looked at the results, while the second team used the wrong tail and then misread what their own measurement result meant. This disagreement leads to two different lessons. The first is that you should always ground your choice of one or two-tailed tests in theory. Whatever you believe will happen before you even look at the results is what's going to inform this decision. The second thing is about interpreting what happens when you can't reject the null. It is not a confirmation that the null is true, it just means you didn't have enough information to reject it. So that's the difference between one and two-tailed tests. The tail choice determines how the p-value is computed. A one-tailed test counts only the probability in one direction which your theory predicts. A two-tailed test counts both directions, which makes the p-value larger and the threshold harder to clear. A one-tailed test is correct when theory gives you a directional prediction before you see the data.